So there are many flow problems over networks that can be formulated as linear programs. And these flow problems over networks find applications in areas such as transportation logistics, routing, and matching. So in today's lecture, we're going to see how we can use linear programs to formulate flow problems over networks. And the class of flow problems over networks that we're going to be talking about today are called the minimum cost network flow problem. So today's topic is going to be the minimum cost network flow problem. We're going to see the minimum cost network flow problem over an example. So let's do that. We're going to talking about minimum cost network flow problem. Okay. So let me try to show you what a minimum cost network flow problem looks like. So we have a network. A network is a bunch of nodes connected with arcs, connected with a bunch of arcs. So let's say I have a network that is composed of node 1, node 2, node 3, node 4, and node 5. Let's say in my network, I have an arc that connects node 1 to node 2, node 1 to node 3, node 3 to node 2, node 2 to node 4, node 3 to node 5, and node 4 to 5, and also node 5 to 4. Okay, so I have a network with 1, 2, 3, 4, 5 nodes, 1, 2, 3, 4, 5, 6, 7 arcs. So my nodes are 1, 2, 3, 4, 5, and my arcs are, I have an arc that connects node 1 to 2, so that's arc 1, 2. I have an arc that connects node 1 to 3, so that's the arc 1, 3. I have an arc that connects node 2 to 4, 3 to 2, 3 to 5, 4 to 5, and 5 to 4. I have 1, 2, 3, 4, 5, 6, 7 arcs. Great. So that's the network setup. I have a whole bunch of nodes connected with a whole bunch of arcs. Some of my nodes are designated as supply nodes. So supply nodes are the nodes that I have availability of product. So let's say node 1 is a supply node with a supply of 5 units. So let's say node 3 is also a supply node with a supply of 2 units. So let's say there's a supply of 5 tons of apples in node 1, and there's a supply of 2 tons of apples in node 2. Okay. And some of the nodes are going to be designated as demand nodes. So let's say node 4 is a demand node with a demand of, let's say, 3 units. And node 5 is a demand node with a demand of 4 units. So node 4 requires 3 tons of apples. Node 5 requires 5 tons of, node 5 requires 4 tons of apples. Okay, so some of our nodes are designated as supply nodes. Node 1 has a supply of 5 tons of apples. Node 2 has a supply of 2 tons of apples. And node 4 and node 5 are designated as demand nodes. Node 4 has a demand of 3 tons of apples, and node 5 has a demand of 4 tons of apples. And associated with each arc, there is a transportation cost. That is the cost of transporting 1 unit of material on each arc. So let's say shipment cost on arc 1, 2 is 5. Shipment cost on arc 1, 3 is 1. Shipment cost on arc 3, 2 is 2. I have a cost of 1 here, 2, 5, and 6. So these are the shipment costs on each arc. So these are the cost of shipping 1 unit of material, 1 unit of 1 ton of apple on each one of these arcs. And our goal is to figure out how to transport the supply of material from the supply nodes to satisfy the demand for the material at the demand nodes, such that we do not violate the supply availabilities at the supply nodes, such that we satisfy the demand requirements at the demand nodes, and also such that we minimize the total cost of the shipments. So that is what a mean cost network flow problem is. We have a network, bunch of nodes connected with a bunch of arcs. Some of the nodes in my network are designated as supply nodes. Some of the nodes in my network are designated as demand nodes. And associated with each arc, there is a unit transportation cost. And in the mean cost network flow problem, I'm trying to figure out how to ship the supply at my supply nodes to satisfy the demand at the demand nodes, such that I don't violate the supply availability at supply nodes. I satisfy the demands at the demand nodes, and in such a way that the total cost of the shipments is going to be as small as possible. So this is the problem that we would like to formulate as a linear program, and this is the problem that is called the mean cost network flow problem. So the main decision, or the decision variable that we're going to use for this problem is going to be amount of material, number of tons of apples, amount of material that is shipped on each arc. So our decision variable is going to be, let's say xij, and that is going to be the flow on arc ij. Okay, so then what are my decision variables? I'm going to have x12, that is the flow on this arc that goes from node 1 to node 2. I have x13, flow on this arc. I have x24, flow on this arc. x32, flow on this arc. x35, x45, and x54. Okay, so those are going to be my decision variables. Good. So before we start, or as we start formulating this mean cost network flow problem, how to ship the supply from supply nodes to the demand nodes to minimize the total cost of the shipments, let's try to understand what a feasible solution to this mean cost network flow problem could look like, so that based on that feasible solution, based on that understanding of that feasible solution, we can try to understand what kind of constraints we are needed in our problem formulation. So let's try to write down, let's try to concoct, let's try to see what a feasible solution to this problem could look like. Let me copy that network one more time here. Okay. I want to see the squaring between these nodes. There you go. This arc, this arc, this arc. Oh, let's go a little bit longer. Okay. And node 1 is a supply of 5. Node 2 is a supply of 2. Node 4 is a demand of 3 units. And node 5 is a demand of 4. Right. So let's see what a feasible solution could look like, so that by looking at that feasible solution, we can understand what kind of constraints we need to write in order to formulate this mean cost network flow problem. Okay. Here's what a feasible solution could look like. I have 5 units of supply in node 1. I have 5 units of supply in node 1. Take those 5 units and ship it along this arc. Okay. So that I have 5 units coming into node 3. I can take those 5 units coming into node 3. Let's say I ship 4 units towards this node and then 1 unit towards this node. Right. So now node 2 has 4 units coming into it. Node 2 has 4 units coming into it. Plus it's got a supply of 2 units in itself. So that gives me a supply of 6 units in node 2. Ship those 6 units towards node 4. So now node 4 has 6 units coming into it. It's got a demand of 3. So out of those 6 units, use 3 to satisfy the demand at node 4 and ship the remaining 3 towards node 5. And node 5 now has 1 unit of supply coming in this direction and 3 units of supply coming in that direction. So node 5 has a total of 4 units coming into itself. So then I'm going to use those 4 units to satisfy the demand at node 5. So that's it. So this is what a feasible solution to my problem could look like. This is what a feasible solution could look like. And again, this is a problem. And this is a problem where the total supply in my network is exactly equal to the total demand. The total supply in my network is 7, 5 plus 2. And the total demand is in my network is 4 plus 3. That's also a 7. So this is a problem where the total supply in my network is exactly equal to total demand, which means that if I need to satisfy the demand at my demand nodes, I need to ship everything out of my supply nodes, right? So the total supply in my network is exactly equal to total demand, which means that if I want to satisfy the demands in my demand nodes, I need to send out all the supply available at my supply nodes out. Okay, good. So this is kind of like a nicely structured, nicely set up problem where the total demand equals total supply, which means that if I want to satisfy the demands, I need to be shipping out all the supplies out of my supply nodes. Okay, so as I said, this is what a feasible solution to this problem could look like. Node 1 has a supply of 5 units. Ship all of those 5 units towards this direction to node 3. So now node 3 has 5 units coming in. Take those 5 units coming into node 3, ship 4 towards node 2, and ship 1 unit towards node 5. So now node 2 has 4 units coming into itself. So node 2 has 4 units coming into itself. Also, node 2 has 2 units of supply in and of itself. So now take the 4 units coming into node 2, and then the supply of 2 units at node 2. That gives me 6 units of supply in node 2. Ship those 6 units towards node 4. So now node 4 has 6 units coming into it. Demand at node 4 is 3 units. So out of those 6 units, use the 3 units to serve the demand in node 4. The remaining 3 units, ship them towards node 5. Node 5 has 1 unit coming in this direction and 3 units coming in that direction, which means that node 5 has a total of 4 units coming into it. So I can use those 4 units to satisfy the demand at node 5, and I'm done. So this is what a feasible solution to my mean cost network flow problem could look like. So based on this understanding, let's try to see what kind of constraints I need to write down. Let's consider a supply node. Let's consider this supply node over here. Let's consider this supply node. For this supply node, I need to ensure that the total flow into the supply node plus the supply at the supply node should be equal to the total flow going out of the supply node, right? So then for a supply node, the constraint I need to write down should say the total flow into the supply node plus the supply available at the supply node should be equal to the total flow going out of the supply node. So now we're going to write a constraint. So let's say for supply node I, we're going to write a constraint that says the following. Total flow into node I plus the supply at node I should be equal to the total flow out of node I. Great. So this is the kind of constraint that I need to write for each supply node I. The total flow coming into the supply node I plus the supply at supply node I should be equal to the total flow coming out of the supply node I. Okay. What do I need to write for a demand node? So let's take a demand node over here. Let's take this demand node 4. Let's take this demand node. What do I need to write for a demand node? For a demand node, the total flow into the demand node should be equal to the demand at that demand node plus the total flow out of that demand node. Let me say it again. What do I need to write for a demand node? So let's take a demand node. The total flow into the demand node should be enough to satisfy the demand at the demand node and the total flow out of the demand node. So for demand node I need to write a constraint that says the total flow into demand node I should be equal to the demand at demand node I plus the total flow out of demand node I. So now for a demand node I, we need to write a constraint that says the following. Total flow into demand node I, total flow into node I should be enough to satisfy the demand at node I, demand at node I, and the total flow out of node I. So these are the constraints that we should be writing for our supply nodes and for our demand nodes. Let's say it again. Let's take this supply node. The constraint that I need to write for supply node I is the total flow into supply node I plus the supply at the supply node I should be enough to cover the total flow out of node I. The total flow into the total flow into supply node I plus the supply at supply node I should be equal to the total flow out of supply node I. Okay. On the other hand, what do I need to write for a demand node? For a demand node I need to write the total flow into node I should be enough to cover the demand at node I and the total flow out of node I. So for a demand node, we need to write total flow into node I is equal to demand at node I and the total flow out of node I. So these are two kinds of constraints that we need to be writing for supply and demand nodes. And you may have some nodes that's neither a supply node or nor a demand node, like node 3 over here. It doesn't have a supply, it doesn't have a demand. So now we need to write a constraint for node 3 that says total flow into node 3 should be equal to the total flow out of node 3. So that should be an exact equality. Inflow should be equal to that constraint should be inflow into node 3 should be exactly equal to the outflow, total outflow out of node 3. Good. So these are the types of constraints that we need to write. Let's organize these constraints a little bit more carefully in the following sense. The total flow into a supply node I is a function of my decision variables. The total flow out of a supply node I is also a function of my decision variables, but the supply at node I is a part of my data. So let me reshuffle this constraint such that everything that's a function of my decision variables are going to be on one side of the constraint, and all of things that are dependent on the data is going to be on the other side of the constraint, so that things are going to be a little bit cleaner. So let's write those constraints on the right-hand side. So for supply node I, let's reshuffle our terms. Total flow out of node I, put this thing to the other side, total flow out of node I minus the total flow into node I is equal to the supply at node I. Total flow out of node I minus total flow into node I is equal to supply at node I. So that's the constraint that I need to write for supply node I. Total flow out of node I minus total flow into node I should be equal to supply at node I. This is the constraint that I need for each supply node I. And likewise, let me reshuffle this constraint for my demand node so that the quantities that depend on my decision variables are going to be on one side of the constraint, and the quantities that are only a function of my data is going to be on the other side of the constraint. So for each demand node I, we're going to write a constraint that says the total flow into node I minus the total flow out of node I is going to be equal to demand at node I. Great. So these are the types of constraints that we need to write in our mean cost network flow problem formulation. So then let's put together our formulation. Let's put together our formulation. I'm minimizing the total cost of the shipments. What decision variable represents the material flow on the arc that goes from node 1 to node 2? X1, 2. For each unit of flow on this arc, I'm incurring a cost of 5. So this is the cost of the shipments on the arc that goes from node 1 to node 2. Likewise, the amount of flow that's in over this arc, X1, 3. X1, 3. And for each unit of flow, I incur a cost of 1, so I'm not going to write that 1. Let's keep going. For each unit of flow on this arc, X24, we're going to incur a cost of 1. For each unit of flow on this arc, X32, we're going to incur a cost of 2. For each unit of flow on this arc, we're going to incur a cost of 6. For each unit of flow on this arc that goes from node 4 to node 5, cost of 2. And lastly, X54 is the amount of flow that goes from that goes on this arc, node 4 to node 5 to node 4, and for each unit of flow on the arc that goes from node 5 to node 4, X54, we're going to incur a cost of 5. So this is the total cost of the shipments that we make. We're trying to minimize. Let's write our constraints. Let's write our constraints. What did we say for our constraints? Let's focus on the supply node 1 here. Let's focus on the supply node 1. I'm looking at a supply node. For the supply node, I'm going to write a constraint that says total flow out of node 1 minus the total flow into node 1 is equal to the supply at node 1. So that's the constraint that I need to write for supply node 1. So let's write this. Total flow out of node 1. I'm writing the constraint for node 1. I'm writing the constraint for node 1, and it's a supply node. I'm writing constraint for node 1, it's a supply node. So we're going to write a constraint that says total flow out of node 1 minus total flow into node 1 is equal to supply at node 1. What is the total flow out of node 1? It's the flow on this arc plus the flow on this arc. So the total flow out of node 1 is X12 plus X13. What is the total flow into node 1? There is nothing flowing into node 1, so that's 0, that's nothing. Is equal to the supply at node 1. The supply at node 1 is 5. That is the constraint that we need to write for node 1. And these types of constraints are called flow balance constraints. So this is the flow balance constraint for node 1. Let's write down the flow balance constraint for node 2. Node 2 is also a supply node. So I'm going to write a constraint for a supply node. So I'm going to use this logic. So I'm writing a constraint for node 2. Again, the total flow out of node 2. I'm writing a constraint for supply node 2. The total flow out of node 2 minus the total flow into node 2 is equal to the supply at node 2. What is the total flow out of node 2? X24. Is there anything else flowing out of node 2? No. So that's the total flow out of node 2 minus total flow into node 2. What is the total flow into node 2? X12, X32. So the total flow out of node 2 minus the total flow into node 2, x1 to x3 2, is equal to the supply at node 2. Supply at node 2 is 2 units. That is the flow balance constraint for node 2. Let's write down the flow balance constraint for node 3. Node 3 is neither a supply or a demand node, so we're going to write a constraint that says total flow out of node 3 is equal to the total flow into node 3. Let's write the total flow out of node 3, x32 plus x35, minus what is the total flow into node 3, that is x13, is equal to 0. So it says total flow out of node 3 is equal to the total flow into node 3. Good. So now let's write the flow balance constraint for node 4. Node 4 is a demand node. Node 4 is a demand node. So the constraint that I'm going to write is going to be of the form total flow into node 4 minus the total flow out of node 4 is equal to demand at node 4. Flow into node 4 minus the flow out of node 4 is equal to demand at node 4. I'm writing the constraint for node 4, and node 4 is a demand node. So the constraint that I'll be writing for node 4 is going to follow this logic, the logic for a demand node. Total flow into node 4 minus the total flow out of node 4 is equal to demand at node 4. So what is the total flow into node 4? The total flow into node 4 is x24 and x54. Total flow into node 4 minus the total flow out of node 4, and that is x45, that is the only arc that leaves node 4, is equal to the demand at node 4, and that is 3 units. So for demand nodes, again, our logic is total flow into the node minus the total flow out of the node is equal to demand at that node. Let's finally write the constraint for node 5. That's also a demand node as well. So now we're going to write the total flow into node 5 minus the total flow out of node 5 is equal to the demand at node 5. So let's write that down. The total flow into node 5, which is x45 and x35, x35 plus x45, the total flow into node 5 minus the total flow out of node 5 is equal to demand at node 5. This is the total flow into node 5. And what is the total flow out of node 5? That is x54 is equal to demand at node 5, that is 4 units. And finally, all of our decision variables are non-negative. Let's just write this in full detail. Okay, all of these decision variables are non-negative. 1, 2, 3, 4, 5, 6, 7. We had 7 arcs. So we have 1 decision variable corresponding to each one of the arcs. So that's my formulation. You take this linear program, solve it through the simplex, get the optimal values of all of these decision variables. At the optimal solution, the value of x12 is going to tell you how much you should be shipping over this arc. At the optimal solution, x32 is going to tell you how much you should be shipping over this arc. x45 is going to tell you how much you should be shipping over this arc, right? So you solve this in your program. At the optimal solution, the values of the x variables for each one of these arcs are going to tell you how much you should be shipping over each one of these arcs. So this is the linear programming formulation of the minimum cost network flow problem. This is the formulation of the problem where we're trying to ship the supplies to satisfy the demands at the demand nodes. We're making sure that we're not violating supply availability at the supply nodes. We're making sure that we're satisfying demand at demand nodes and minimizing the cost of the shipments. Okay. And this formulation again uses the fact that the total supply in the network 7 is equal to total demand in the network 7. As a result, in order to be able to serve my demands, I need to be shipping everything out of my supply nodes. So in this formulation, we're exploiting that. Towards the end of the lecture today, we're going to see how we can tweak these kinds of formulation when we have more supply than we need. Good. Okay, this formulation is going to do the job. But one of the things that I don't like about this formulation is that for the supply node and for the demand node, I need to try kind of like different types of formulas, right? For the supply node, for the supply node I, we need to write a constraint that says the total flow out of node I and the total minus total flow into node I is equal to supply at node I. So that's what I need to write for a supply node. The total flow out of node I minus the total flow into node I is equal to supply at node I. On the other hand, for demand nodes, I need to write the total flow into node I minus the total flow out of node I is equal to the demand at node I. So I need to write different left-hand side, out minus in for supply nodes, in minus out for the demand nodes. And I don't want to memorize that. I don't want to keep that in mind all the time. So let's try to tweak our formulation a little bit so that we do not need to do this memorization all the time. And here's how we're going to tweak our formulation a little bit. Take the formulation of the minimum cost network flow problem that we had before. Keep the constraints for the supply and the intermediate nodes as they are. Take the constraints for the demand nodes and write them by multiplying these constraints by negative. So I'm going to write the same formulation. The only difference is going to be that we're going to multiply these flow balance constraints for the supply nodes by -1. And let's see what that gives us. That's going to make things a little bit more pretty, actually. Keep the objective function as it is. My 5x12, 1x13, 1x24, 2 times x32, 6 times x35, 2 times x45, and 5 times x54. Keep the objective function as it is. And keep the flow balance constraint for the supply and the intermediate nodes as they are. x12 plus x13 equals 5. x24 minus x12 minus x32 equals 2. x32 plus x35 minus x13 equals 0. So now let's write these constraints by just multiplying them by -1. So if I multiply this constraint by -1, I'm going to get x45 minus x24 minus x54 is equal to -3. I just write this constraint by multiplying both sides by -1. Plus x45 minus x24 minus x54 equals -3. Let's also write this constraint by multiplying both sides by -1. If I do that, we're going to get x54 minus x35 minus x45 equals -4. And we have the non-negativity constraints on all of our decision variables. Let me just write it in full detail. Good. Why did we do this? What did we accomplish by doing this? So now let's read the form of these flow balance constraints. Let's look at the flow balance constraint for node 1. Let's look at the constraint for node 1. Let's look at the constraint for node 1. What are we saying? x12 plus x13. That is the flow out of node 1. There is no flow into node 1. That's 0. That's flow out of node 1 is equal to the supply at node 1. All right. Let's look at the constraint for node 2. x24. That is the flow out of node 2. Minus x12 and x32. That is the flow into node 2, right? x12, x32. x24, that is the flow out of node 2, minus x12 and minus x32. So that's minus total flow into node 2 is equal to supply at node 2. So both of these constraints are of the form total flow out minus total flow in is equal to the right-hand side of the constraint. How about this constraint? Let's get the constraint for node 3. x32 plus x35, that is the total flow out of node 3, minus x13, that is the total flow into node 3, is equal to the some number on the right-hand side. So all of those constraints are of the form so far, out minus in, out minus in, out minus in. If I look at the constraint for node 2, for example, again, x24, that is the flow out of node 2, minus x13, minus x32, minus x12, minus x32, that is going to be the total flow in. So all of these constraints so far are of the form out minus in. Let's look at this constraint now. Constraint for node 4. x45. x45 is the flow out of node 4. What is this constraint? Minus x24, x54. That is the total flow into node 4. So now this constraint is of the form out minus in, but it just happened that the right-hand side of the constraint is a negative number. Okay. Let's get what we have for this constraint, flow balance constraint for node 5. x54. x54 is the flow out of node 5. That's flow out. Minus x35 and x45. x35, x45, that is flow in. So this constraint is of the form out minus in. So when we write the constraints in this way, the left-hand side of the constraints are always of the form total flow out minus total flow in equals some number on the right-hand side, and the number on the right-hand side is positive for the supply nodes and negative for the demand nodes. So this kind of like cuts down all the memorization that we need to do. Our constraints, the left-hand side of the constraints are always of the form total flow out minus total flow in equals some number on the right-hand side, and the number on the right-hand side is positive for the supply nodes and negative for the demand nodes. Great. So that makes our formulation a little bit more uniform, a little bit easy to keep in mind. So let's say then for all nodes I, if you formulate the mean cost network flow problem in this fashion, the constraints that we have is of the form total flow out of node I minus total flow into node I is equal to, let's call this number the availability at node I. And for supply nodes, the availability is a positive number. For demand nodes, the availability is a negative number. For the intermediate nodes, the availability is a 0. Is equal to availability, let's say, at node I. And availability is positive for supply nodes, negative for demand nodes, and 0 for others. This is a little bit more uniform formulation of the mean cost network flow problem. Okay, so our constraints, our flow Wales constraints are always going to be of the form total flow out of node I minus total flow into node I equals to the availability at node I. And availability at node I is a positive number when we're looking at a supply node. Availability at node I is a negative number when we're looking at a demand node. So this is going to make things a little bit more uniform, a little bit easier to remember. Okay. Good. Again, you solve this linear programming formulation. The optimal values of these x variables are going to tell you how much flow we should be sending over each one of these arcs to minimize the total cost while satisfying the demands. Good. So there is one super useful thing about the mean cost network flow problem, and that is the following. This is a mean cost network flow problem where the supply and the demand quantities are integer valued. Right? We have 5, 2, these are integer values, 3, 4, these are integer values. One of the beautiful properties of the mean cost network flow problem is that if you have a mean cost network flow problem where all the supply and all the demand quantities are integer valued, then if you solve this problem by using the simplex method, the optimal solution is always going to be an integer valued solution. Okay, we're not going to do a proof of this fact. But it comes from the fact that if you solve the mean cost network flow problem by using the simplex method, the simplex method never has to do divisions or multiplications. It only does additions and subtractions. And if you're doing only additions and subtractions during your row operations, adding the integer right-hand side or subtracting integer right-hand side is always going to give you integer right-hand side. That's where that one is coming from. And that is a beautiful property. In general, if you have a linear program, where the right-hand sides are all integers, it is not guaranteed that the optimal solution is going to take integer values for the x's. In general, if you have a general linear program where all the right-hand sides are integers, you don't know. You cannot guarantee that the optimal solution take integer values. But the beautiful thing about the minimum cost network flow problem is that if all the supply and the demand data are integer valued, if you solve this problem using the simplex method, you're guaranteed that an optimal solution, you're going to hit an optimal solution with integer values for your x variables. Okay, and again, that's coming from the fact that when you do simplex on this nicely structured problem, simplex algorithm only does additions and subtractions. It never does multiplications or divisions. Okay. And why is that property useful? Well, if you're shipping tons of apples, maybe having fractional quantities is not a big deal. I could be shipping, 2.768935 tons of apple on a particular arc. But if you're shipping cars, if you're shipping buses, if you're shipping computer servers, whatever it is, then in that case, it is imperative. It's important that you should be shipping integer quantities. You don't want to come up with a solution where you ship half a car this way, half a car this way, 1/3 of a car this way, 2/3 of a car this way. So again, one of the beautiful, very peculiar properties of the mean cost network flow problem is if all of your supply and the demand data are all integers, simplex, the optimal solution that's going to return by the simplex when you solve this in your program is going to have all the x variables integer quantities. This doesn't require the cost coefficients to be integers. Cost coefficients can be fraction. As long as your supply and demand data are integers, there's going to be an integer optimal solution to this problem. Good. Okay, so now we know how to write down a mean cost network flow problem. But when you're dealing with a mean cost network flow problem over a network with hundreds of thousands of arcs and thousands of nodes, it is going to be difficult to write down this formulation for every arc and for every a constraint for every node in your network. So let's try to write down a compact formulation of the mean cost network flow problem. So how do you write this formulation in a compact form? Compact formulation of the mean cost network flow problem. Great. When we write a compact formulation for a linear program, the first thing we do is we characterize our data. What is the data for our mean cost network flow problem? One piece of the data is the set of nodes. So let's say n is going to be our set of nodes. Good. Another piece of data is going to be the set of arcs. So let me use V to be the set of arcs in my network. Okay. Here in this example, the set of nodes are 1, 2, 3, 4, 5. The set of arcs are 1, 2, 1, 3, 2, 4, 3, 2, 3, 5, 4, 5, 5, 4. Okay, good. What other data do we have for our mean cost network flow problem? Another data we have is the cost of shipment over each one of these arcs. So let's say C sub ij is the cost of shipping a unit on arc ij. So those are the shipment costs on each one of the arcs in the network. And lastly, what is the last piece of data that we need for our mean cost network flow problem? It's the supplies and the demand quantities. To capture them together succinctly, let's say SI is the availability at node I. And availability at node I is positive for supply nodes, negative for demand nodes, and 0 for the other nodes. Okay, so this is all the data that we have for this is all the data that we have for the mean cost network flow problem. Set of nodes, set of arcs, cost of shipping one unit on arc ij, Cij, and SI is the availability at node I. SI is a positive number for a supply node, SI is a negative number for demand node, and 0 for the intermediate nodes. Good, so that's the data. Good. What is our decision variables? That is x sub ij, x sub ij, flow on arc ij. And for every arc ij, in my arc set, I have a decision variable xij. For every arc ij in my arc set, I have a decision variable ij. Good. So now, how do we write our flow balance constraints? Remember, how do we write our flow balance constraints? In this uniformized fashion, we said we're always going to write the flow balance constraint as total flow out of node I minus total flow into node I is equal to the availability at node I, right? Total flow out of node I minus total flow into node I is equal to the availability at node I. Total flow out of node I minus total flow into node I is equal to the availability at node I. So then in this general formulation, this compact formulation, how do we write the total flow out of node I? Let's think about that. How do I write the total flow out of node I? So here's I have node I. Here's I have node I. From node I can go to node J. And the flow on that arc is Xij. From node I can go to node K. The flow on that arc is Xik. From node I can go to node L. The flow on that arc is Xil. So the total flow out of node I is Xij plus Xik plus Xil, blah, 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 blah. Okay. So if I want to write the total flow out of node I, what I need to do is for fixed I, add over Xij variables over all the J's. Okay. So if I want to write the total flow out of node I, we're going to write something like this. Take the xij variables for node I added over all j's in my node set, added over all j's in my node set, such that ig is a valid arc. Ig is a valid arc in my network. Okay, so this is the sum over xij's for a fixed size, sum over xij's over aj over all j's, such that ig is a valid arc in my network. So this is how we're going to write the total flow out of node I. If I want to compute the total flow out of node I, from node I can go to node j, that's xij. From node I can go to node k, that's xik. From node I can go to node l, that's xil. So if I want to compute the total flow out of node I, xij plus xik plus xil, blah, 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 all these things added up. So if I want to compute the total flow out of node I need to add up xij variables over every j for fixed I. So if I want to compute total flow out of node I need to add up xij variables over every j for fixed I. And I need to add up these xij variables over every j's such that over every node j such that ij is an arc in my network. So that's how we can write succinctly the total flow, or in compact form, the total flow out of node I. Likewise, let's think about how we can write the total flow into node I. Let's throw a similar picture. So I'm trying to write the total flow into node I. Here's my node I. Total flow into node I. I can come to node I from node j. The flow is here, xji. I can come to node I from node k. The total flow over here is xki. I can come to node I from node L. The flow here is xli. So if I'm trying to write the total flow into node I, I can come to node I from node j. I can come to node I from node k. I can come to node I from node L. So I'm going to add up xji plus xki plus xli, blah, 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 blah. All these things added up. So if I want to write the total flow into node I, for fixed I need to add up all of the decision variables of the form xji over every j. So now let's write total flow into node I. If I want to write the total flow into node I, what we're going to do is add all the decision variables of the form xji over every j that is a node, such that ji is a valid arc in my network. So this is how we write the total flow into node I. Okay, so now I know how to write in compact form total flow out of node I and the total flow into node I. So now we can write our mean cost network flow problem in compact form. If you want to write the mean cost network flow problem in compact form, minimize the total cost. This is the flow on arc ij. For each unit of flow on arc ij, we're incurring a cost of cij. So that's the cost of the flow on arc ij, added over all arc. That is in my arc set. So this is the total cost that we're trying to minimize. Okay. Our flow balance constraint is going to be of the form total flow out of node I minus total flow into node I is equal to the availability at node I. Let's write this down. Let's do it like this. Total flow out of node I minus total flow into node I is equal to the availability at node I. Here's the total flow out of node I. Minus total flow into node I, xji, such that ji is an arc, is equal to the availability at node I, and that's our notation for availability at node I. And we have one of these flow balance constraints for every I, for every node in my network, for every node I in my network, and my set of nodes is n. And lastly, all of our decision variables are non-negative. Let's write the non-negative constraints for our decision variables. Xij is greater than or equal to 0. And I have a decision variable for every arc ij, and my set of arcs is V. Okay, so this is the nice, clean, compact formulation of the mean cost network flow problem. I have a decision variable xij. I have a decision variable xij for every arc in my network. I have a decision variable xij for every arc in my network, multiplied by the corresponding unit shipping cost on that arc, added over all arcs. This is the cost that I'm trying to minimize. And in the constraint, we have one flow balance constraint for every node I in the network. We have one flow balance constraint for every node I in the network. And that's written as total flow out of node I minus total flow into node I is equal to the availability at that node. And all of our decision variables are non-negative. This is a simple, clean, compact way of writing the mean cost network flow problem. No matter how large, no matter how many nodes you have, no matter how many arcs you have, this formulation stays as it is. It doesn't matter. Okay. So then let's now think about, in the example that we looked at, in the formulations that we looked at so far, the total supply was exactly equal to total demand, so that if you wanted to serve the demands, you had to ship everything out of the supply nodes. So now let's look at an example where the total supply is not exactly equal to the total demand. And let's try to understand how we can tweak our formulation, okay, to handle that case. Let's say how to deal with the case. How to deal with the case when total supply is not equal to total demand. Okay, let's take an example. Let's tweak our previous example a little bit. Node 1, let me just put a little bit of I want space. Node 1, node 2, 3, 4, 5, more or less the same network. Let's now put a supply of 6 units in node 1. Let's put a supply of 3 units in node 2. Let's put a demand of 3 units in node 4. And let's put a demand of 4 units in node 5. Okay. What is the total supply in my network now? What is the total supply in my network? It's 9 units. The total demand in my network is 7 units. So I have more supply than the demand. Then to satisfy the demand, I don't need to ship everything out of my supply nodes. I can keep some of the material in my supply nodes while still satisfying the demand nodes. And the optimization problem is going to decide whether I should be keeping some of the supply at this supply node or keeping some of the supply at this supply node. It's subject to optimization, whatever best turns out to be. Good. Let's put the unit transportation costs on these arcs as well. So it's in front of us. 1, 5, 2, 1, 2, 5, 6. Good. So now let's try to think about what kind of a constraint we need to write when the total supply is greater than the total demand. Okay. Here's how we're going to write. Let's focus on a supply node I. For a supply node, we need to write a constraint that says the following. For a supply node, we need to write a constraint that says the following. Total inflow into node I. For a supply node I, we need to write a constraint that says the following. Total flow into node I plus the supply node I should be enough to cover total flow out of node I. Okay, so what we're going to write for a supply node I is the following. Total flow into node I plus the supply at supply node I should be enough to cover what is flowing, should be enough to cover the total flow out of node I. So we're going to write a constraint that says total flow into supply node I plus the supply at supply node I should be greater than or equal to the total flow out of node I. So now for supply node I, we're going to write a constraint that says the following. Total flow into node I plus the supply at node I should be enough, should be greater than or equal to the total flow out of node I. Okay. So when total supply in network is greater than the total demand, then the constraint we need to write is going to be of the form. For a supply node, we need to write a constraint that says total flow into node I plus the supply into that node should be enough to cover the total flow out of node I. Total flow into node I plus the supply at node I should be greater than or equal to the total flow out of node I. And let's write it again of the form such that the right-hand side of the constraint is always of the form total flow out minus total flow in. So then put this number, throw it to the right-hand side. So it's going to be total flow out of node I minus the total flow into node I is less than or equal to supply at node I. So then this constraint is equivalent to, no, I'm not going to put this down here. I don't like it right now. So this constraint is equivalent to, let me take this term, throw it to the right-hand side. Total flow out of node I minus total flow into node I, so I throw this to the other side, is less than or equal to supply at node I. So this is how we need to tweak our formulation when we're dealing with the case total supply exceeds the total demand in the network. Okay, good. So based on this, let's tweak our formulation. Let's write our mean cost network flow problem. Minimize the total cost of the shipments. 5 times x12 plus 1 times x13 plus 1 times x24 plus 2 times x32 plus 6 times x35 plus 2 times x45 plus 5 times x54. Okay, good. So now for our supply nodes, what kind of a constraint are we writing? For our supply nodes, what kind of a constraint are we writing? Total flow out of node I minus total flow into node I is less than or equal to supply at node I. Okay? Total flow out of node I minus total flow into node I is less than or equal to supply at node I. Let's write it. For the first node, what is the total flow out of node I? x12 plus x13. Total flow, we're writing the flow balance constraint for node 1. It's a supply node. So we're writing a constraint that says total flow out of node 1 minus the total flow into node 1 is less than or equal to supply at node 1. Total flow out of node 1, that's it. There is no flow into node 1 is less than or equal to the supply at node 1. That's a 6. Let's write the flow balance constraint for node 2. Node 2 is a supply node. Node 2 is a supply node. So now we're going to write a constraint that again says total flow out of node I minus total flow into node I is less than or equal to supply at node I. Total flow out of node I, x24, minus the total flow into node I, x12, x32, minus x12 minus x32 is less than or equal to supply available at node I. That's 3 nodes. Okay. My other nodes are either intermediate nodes or demand nodes, so those things don't change. The flow balance constraints for those nodes don't change. We always write total flow out minus total flow in equals the availability at the node. Let's write the constraint for node 3. Total flow out, x32 plus x35, total flow out, minus total flow in, minus x13, is equal to the availability at node 3, that's a 0. Let's write the constraint for node 4. Total flow out, x45, minus total flow in, x24 and x54. Is equal to the availability at this node. What is the availability at this node? It's a -3 because it's a demand node with a demand of 3. Keep going. And lastly, for constraint 5, we're going to write total flow out minus total flow in equals the availability. Total flow out is x54 for node 5. Total flow out is x54 minus total flow in is x45 and x35. Let's write x35 and x45. So I'm writing the flow balance constraint for node 5. It's written as total flow out minus total flow in. Total flow out is x54 minus total flow in is minus x35 minus x45. That is the availability. That's equal to the availability at node 5. What is the availability at node 5? That is -4. And again, all of our decision variables are non-negative. Okay. So this is how we deal with the case where the total supply in the network exceeds the total demand availability. Okay, good. So this gives us a complete package. This is a good point to stop the discussion. What did we today? We talked about the mean cost network flow problem. Mean cost network flow problem is formulating a flow problem over a network by using a linear program. And in this formulation, we have an objective function, which is the total shipment cost over all of the arcs, and subject to a whole bunch of flow balance constraints. And the type of the flow balance constraint is always of the form total flow out of node I minus the total flow into node I is equal to the availability at node I when the total supply equals total demand. Okay, so when the total supply equals total demand, the form of the flow balance constraint is always of the form total flow out of node I minus total flow into node I is equal to the availability at node I. And availability at node I is a positive number for supply nodes, negative number for demand nodes, and 0 for the intermediate nodes. Okay, in the next lecture, we're going to look at all these different applications of the mean cost network flow problems. Let's stop here.